Welcome back to the deep dive. Today, we're going to dive into alcohols, phenols, and ethers.
Sounds exciting.
Yeah,
Yep.
these are like, compounds that sound all fancy and textbooky, but really they're all around us all the time. It's kind of cool when you think about it. We're going to uncover like the secret lives of these everyday molecules.
Exactly.
From like the antiseptic sting of rubbing alcohol to the sweet smell of vanilla. I mean, these things are more than just, formulas on a page. They're part of like our daily lives.
Definitely.
So to guide us on this little adventure through the world of molecules, we have our expert. So what's the big picture? What makes these compounds so interesting?
Well, the fascinating thing about alcohols, phenols, and ethers is that they all have this basic hydrocarbon skeleton, and they get their unique properties from these little chemical tags. We call them functional groups.
Okay.
Alcohols and phenols have what we call a hydroxyl group. It's just an oxygen and a hydrogen atom bonded together.
Okay.
And then ethers have an oxygen atom that's linked to two carbon groups.
So it's like these functional groups are like accessories for the molecules. Give them each their own little personality.
Yeah, that's a great way to put it.
But I'm seeing all these different types of alcohols and phenols in our notes here. We've got mono and diol and tri and even polyhydric versions. Can we break those down a bit? What are all those?
Absolutely. Imagine you're building with Legos.
Okay, I like Lego.
A monohydric alcohol, it has just one hydroxyl group attached to that carbon backbone, like a single Lego brick.
Okay, I get it.
Then you have your dihydric alcohol. It's got two hydroxyl groups, like two Lego bricks snapped together,
Yeah.
and so on and so forth. You go all the way up to polyhydric alcohols, and those are like those crazy Lego creations with like tons of bricks all linked together.
So like a sugar molecule with a whole bunch of hydroxyl groups would be like, what, a massive Lego castle or something.
Exactly.
No wonder it gives us so much energy. But okay, let's go back to those like single brick alcohols for a second. I'm guessing there are like different types even within just those.
Yeah.
Right?
Oh, definitely. Even with just your monohydric alcohols, we can classify them further based on what that carbon atom with the hydroxyl group is attached to. So if it's attached to one other carbon atom,
Yeah.
that's a primary alcohol.
Right.
If it's attached to two other carbons, secondary alcohol. 3, that's a tertiary alcohol.
So it's like a family tree for molecules with different branches based on how the carbons connect. But how do we even keep track of all these different compounds? Like, do we just call them like single brick alcohol with 2 carbons? Or triple brick alcohol with a fancy ring or something?
Thankfully, no. We've got naming systems to help us keep things straight.
Oh, good.
There are common names, they're like nicknames, but for, real chemistry, we use the IUPAC system.
IUPAC, huh?
Yeah, it's a set of rules for naming compounds so that everyone, understands what we're talking about.
So it's like the IUPAC is the official language of chemistry. Everyone's on the same page no matter where they're from.
That's a great way to put it.
Okay, cool.
For alcohols, the IUPAC name always starts with the name of the parent hydrocarbon chain. Then you just swap out that E at the end with ol to show it's an alcohol.
Oh, okay.
Like, for example, you have methane, the simplest hydrocarbon. It becomes methanol when it gets that hydroxyl group.
So it's like adding ol is like giving it a molecular stamp. It says, hey, I'm an alcohol now.
Yeah, exactly.
But I bet it gets a bit more complicated when you have, more complex molecules.
Of course. With more complex structures, we use numbers to pinpoint where the hydroxyl group is, and any other, side groups on the carbon chain, we got to be precise.
So like giving each part of the molecule its own little address so we know exactly where it lives.
Yes, precisely.
What about those big Lego castles with multiple hydroxyl groups? Do we need a special way to say, like, how many hydroxyl groups are there?
We do. We use prefixes, di, tri, and so on,
Oh, okay.
to show how many hydroxyl groups we're dealing with. So say you have 2 hydroxyl groups attached to an ethane molecule.
Uh-huh.
That would be ethane 1-year-2-diol.
Okay, so it's like a molecular head count, making sure we know exactly how many hydroxyl groups are in each compound.
Precisely.
This is making sense.
Yeah.
But hold on, we haven't even talked about phenols and ethers yet.
Yeah.
Do those have similar naming rules?
Phenols have their own little quirks in the naming system.
Oh, okay.
The simplest one is just called phenol. But when you start adding other groups to that benzene ring, we use terms like ortho, meta, and para to show their position relative to the hydroxyl group.
Wait, are we talking about molecular seating arrangements now? Like ortho is next to the hydroxyl group, meta is 1 seat over, and para is across the table.
You got it. That's a great way to think about it.
So we've got alcohols with their ol ending, phenols with their ortho, meta, para thing, and ethers, we'll get to them. But I'm wondering, how do all these names actually connect to what the compound looks like? It can't be just random atoms all jumbled together, right?
Oh, no, there's definitely an underlying order to it all. The structure of these compounds is what dictates their properties and how they interact with, the world around them.
Okay.
For alcohols, the oxygen atom in that hydroxyl group, it's bonded to a carbon atom by a single bond. It's called a sigma bond.
Sigma bond, is that like super glue for molecules?
You could say that. It's a really strong bond that forms when electron orbitals overlap.
Overlap.
Electron orbitals are like, regions around the atom where you're likely to find electrons.
So it's like these electron orbitals are reaching out and holding hands to create that bond between the oxygen and the carbon.
Exactly.
But what about those, the oxygen atom has those two lone pairs of electrons. Do they just like hang out, or do they actually do something in the molecule's structure?
Oh, those lone pairs, they are definitely not just sitting around. They have a big impact on the molecule's shape.
Oh, how so?
Because those electron pairs, they repel each other, right? They end up pushing the bonds a little bit away from that perfect tetrahedral angle.
Okay.
It's supposed to be 109.5 degrees.
It's like the electron pairs need their space. They're pushing those bonds out of their ideal positions.
You got it. And even that little distortion in the bond angles changes how these alcohols interact with other molecules.
Wow, so even tiny changes in a molecule's shape can have like a ripple effect on how it behaves.
Exactly.
What about phenols and ethers? Are they different in terms of structure?
In phenols, the hydroxyl group is attached to a carbon that's part of that benzene ring, and that ring structure changes the bond lengths and angles. The carbon-oxygen bond in phenols is actually a bit shorter than in alcohols.
So like the benzene ring is a bit of a space saver, pulling those atoms closer.
And then in ethers, the oxygen atom is bonded to two carbon groups, those lone pairs of electrons. They're still there, influencing the shape.
Right.
So they create like a roughly tetrahedral arrangement around the oxygen atom, but the angle's a bit bigger than that ideal 109.5 degrees because the carbon groups are bulkier.
So it's like those carbon groups need more elbow room, pushing the bonds further apart.
Exactly.
It's crazy how these little differences in structure can actually change the properties of a molecule and how it interacts with the world. But so far, we've just focused on how they look and how we name them. I want to know how we actually make these things. It can't be as easy as just throwing a bunch of chemicals in a beaker and hoping for the best.
No, it's a bit more complicated than that. Chemists have actually come up with very specific ways to make alcohols, phenols, and ethers.
Oh, okay.
And each method has its own little, quirks and advantages depending on what type of compound you're trying to make.
It's like a molecular cookbook.
Yeah.
Different recipes for each compound.
Yeah, exactly. And just like with cooking, using the right ingredients and following those steps carefully is really important for getting what you want.
All right, so let's get cooking. Where do we start with this molecular recipe book?
Let's start with alcohols. One way to make them is to start with an alkene.
Alkene.
Yeah, it's a hydrocarbon with a carbon double bond. You can add water to that double bond. You need an acid catalyst, though, and boom, you get an alcohol. We call that acid-catalyzed hydration.
So it's like giving the alkene a little drink of water and it magically transforms into an alcohol. But what happens if you have, an unsymmetrical alkene, like where the groups on those double-bonded carbons are different? Does the water just, pick a side at random?
Well, that's where a rule called Markovnikov's rule comes.
Markovnikov's rule.
Yeah, it helps us figure out where that hydroxyl group is going to add to the double bond. It basically says that the hydroxyl group prefers to attach to the carbon that already has more hydrogens attached to it.
So it's like the hydroxyl group wants to go where the party's at. Join the most crowded group.
That's a great way to think about it.
Are there any other ways to make alcohols besides this hydration method?
Yes. Another method is called hydroboration oxidation.
Okay.
It's a two-step process that uses a boron compound and hydrogen peroxide.
Uh-huh.
What's interesting is this method actually gives you the opposite result to Markovnikov's rule. Oh.
The hydroxyl group ends up on the less substituted carbon.
It's like the hydroxyl group is going against the flow, choosing the less crowded party this time.
Exactly. It shows how we have different tools for manipulating these molecules. Each one gives us a different result.
So cool. It's like we're learning the secret language of chemistry, but we still haven't talked about how to make phenols or ethers. I'm really curious about those recipes.
All right, let's move on to phenols then. Remember, phenols are those compounds where the hydroxyl group is directly attached to a benzene ring. One way to make them is to start with halorenes.
Halorenes.
Yeah. Those are benzene rings with a halogen atom attached, like chlorine or bromine.
Okay.
You can react a halurene with sodium hydroxide at high temperature and pressure. What happens is you basically swap the halogen for a hydroxyl group, and ta-da, you have a phenol.
So it's like a molecular switcheroo, out with the halogen, in with the hydroxyl. Are there any other ways to make phenols? Yep, several. We can also start with benzene sulfonic acid, which is benzene with a sulfonic acid group. You react that with molten sodium hydroxide and then acidify it, and you get phenol. Or another method is to use diazonium salts. Those are organic compounds with a nitrogen triple bond.
All right.
When you hydrolyze a diazonium salt, you replace that diazonium group with a hydroxyl group, and you get phenol.
Wow, so many paths to the same destination. What about that, the phenol we use for all sorts of things? Is there a special way that's made on like an industrial scale?
You're right. Actually, most of the phenol used commercially is produced from cumene.
Cumene.
Yeah, it's a hydrocarbon. You oxidize cumene to get cumene hydroperoxide, and then you treat that with a dilute acid to get phenol and acetone as a bonus. 2 for the price of 1.
It's like a buy one, get one free deal at the molecular market.
Yeah.
But we still haven't gotten to ethers. How do we make those?
Ethers are interesting because one way to prepare them is through dehydration of alcohols. Remember how we talked about dehydrating alcohols to make alkenes? Yeah. Well, if you tweak the conditions a bit, you can actually get ethers instead.
Wait, so alcohols can lose water to form both alkenes and ethers. What's the secret? How do you choose which one you get?
It really comes down to the reaction conditions, the temperature you use, and what type of alcohol you're starting with.
Okay.
If you really crank up the heat, you'll probably get an alkene. But if you keep things a bit cooler and use a primary alcohol, you're more likely to get an ether.
So it's like a molecular balancing act. We can adjust those conditions to kind of nudge those molecules toward what we want. But is there another way to make ethers, one that's maybe a bit more, I don't know, straightforward?
Yeah, there's a method called Williamson synthesis.
Williamson synthesis, okay.
That's our go-to for making ethers, whether they're symmetrical or not. In this reaction, you have an alkyl halide. It's an alkene with a halogen attached, and it reacts with something called a sodium alkoxide.
Sodium alkoxide.
Just think of it as an alcohol that's lost its hydrogen and replaced it with a sodium atom. Oh. What happens is the alkyl halide basically swaps its halogen for the oxygen from the alkoxide. And bam, you've got your ether linkage.
So it's like a molecular trading post.
Yeah.
They swap partners, and an ether is born.
This is so cool. We're actually manipulating these molecules to get what we want.
It is pretty amazing, and this is just the beginning. There's a whole world of fascinating chemistry going on behind these seemingly simple compounds.
This is already blowing my mind. We've explored how alcohols, phenols, and ethers are named, how their structures work, and even how we can make them. But I'm curious now, how do their properties change based on those structural differences? Like, do those little tweaks in how they're put together actually mean anything in the real world?
Absolutely. That arrangement of atoms has a huge impact on how they behave. Let's talk about boiling points, for example. You'll notice that alcohols and phenols tend to have higher boiling points compared to ethers or hydrocarbons with a similar molecular weight.
Why is that? It all has to do with those hydroxyl groups. Alcohols and phenols can form hydrogen bonds, which are pretty strong attractions between molecules.
Okay.
It's like these tiny magnets holding those molecules together, so it takes more energy to break them apart, hence the higher boiling point.
So those hydroxyl groups are like molecular glue, keeping the molecules stuck together.
Exactly.
What about solubility? Do they mix well with water, these alcohols, phenols, and ethers?
Well, that depends.
On what?
Whether or not they can form hydrogen bonds with water molecules.
Oh, okay.
Alcohols and phenols, especially the ones with smaller alkyl or aryl groups, tend to be quite soluble in water because those hydroxyl groups can hydrogen bond with those water molecules.
So it's like the hydroxyl groups are introducing the alcohol or phenol to the water, helping them mix and mingle.
Exactly.
But the size of that alkyl or aryl group probably matters too, right?
It does. The bigger that group gets, the less soluble the compound becomes in water. It's like trying to mix oil and water. They just don't want to hang out together.
This is fascinating. Those tiny structural differences make such a big difference. What about how they react with other chemicals? Do those hydroxyl groups and ether linkages make them more reactive or less reactive?
That's a great question. The reactivity of alcohols and phenols, comes down to that hydroxyl group. They can act as both nucleophiles and electrophiles.
Nucleophiles, electrophiles, huh?
Yeah, meaning they can either donate electrons to form a new bond, or they can accept electrons.
So they're like, what, molecular chameleons adapting to whatever reaction they're in?
Exactly. A very good analogy.
But what about ethers? Are they as reactive as alcohols and phenols?
Ethers are actually way less reactive than alcohols and phenols.
Oh, okay.
Those carbon-oxygen bonds in ethers, they're pretty stable. They don't break easily.
So they're like the quiet ones in the family, not really into all the reacting and stuff.
Well, that's a good way to put it.
But let's get back to alcohols and phenols for a minute. You mentioned their acidity. What does that even mean? Are we talking like lemon juice levels of acidity here?
Yeah. Not quite that sour, but alcohols and phenols can donate a proton, a hydrogen ion, to a stronger base.
Okay.
And it's that ability to donate a proton that makes them acidic.
So they're like tiny little proton dispensers.
Exactly.
But are they all the same level of acidity, or are there differences between alcohols and phenols?
Phenols are actually more acidic than alcohols.
Oh, okay. Why is that?
It's because of that benzene ring. The OH group in phenols is attached directly to the ring, and that ring acts as what we call an electron withdrawing group, which makes it easier for the phenol to lose its proton.
So it's like the benzene ring is kind of greedy, pulling those electrons away from the OH group and making it more willing to give up its proton.
Precisely.
Are all phenols the same level of acidic then, or are there things that can change how willing they are to give up that proton?
Good question. The presence of other electron withdrawing groups on that benzene ring, like nitro groups, actually increases the acidity of phenols.
So it's like adding another greedy friend to the mix, making that OH group even more eager to get rid of its proton.
Exactly.
What about like electron-releasing groups, things like alkyl groups? Do they have the opposite effect?
You got to electron-releasing groups actually decrease the acidity of phenols.
Oh, interesting.
They're like the generous friend donating electrons to that OH group, making it less likely to give up its proton.
So it's a real tug-of-war then between those electron-withdrawing and electron-releasing groups.
That's a great analogy.
Okay, but let's move on to reactions. You mentioned something called esterification earlier. What's that all about?
Esterification is a really cool reaction where alcohols and phenols react with carboxylic acids to form esters.
Esters, okay.
And esters are these compounds with a really characteristic fruity smell. They're what give a lot of fruits and flowers their flavor.
So they're like the perfume masters of the molecular world.
You could say that.
But how do alcohols and phenols actually make these fragrant esters?
Well, the OH group of the alcohol or phenol reacts with the carboxylic acid group, and that forms the ester and a water molecule. This reaction is usually catalyzed by a strong acid like sulfuric acid.
It's like a molecular dance.
Yeah.
The alcohol or phenol and the carboxylic acid swirling around together with this strong acid chaperone, and they create a beautiful scented ester.
I love that analogy.
Are there any specific reactions that alcohols do that phenols don't?
Yes. One important reaction is the reaction of alcohols with hydrogen halides, like hydrogen chloride or hydrogen bromide. They form alkyl halides.
Alkyl halides, what are those?
Alkyl halides are just alkenes with a halogen atom attached. It's basically a way to change alcohols into compounds with different functional groups, opens up a whole new set of possibilities.
So it's like giving alcohol a whole new personality.
Exactly.
Any other cool reactions that alcohols do?
Absolutely. Alcohols can also go through something called dehydration, where a water molecule is removed from the alcohol molecule and you get an alkene. Remember how we talked about using dehydration to make ethers? Well, under different conditions, you can actually use dehydration to make alkenes instead.
So it's like choosing your own adventure at the molecular level. We can tweak those reaction conditions to make either ethers or alkenes.
Exactly.
But are all alcohols equally easy to dehydrate, or does it depend on their structure?
That's a great question. The ease of dehydration depends on whether the alcohol is primary, secondary, or tertiary. Tertiary alcohols are the easiest to dehydrate, followed by secondary, and then primary are the hardest.
Is it because tertiary alcohols are like the rebellious teenagers of the alcohol family? They just want to shed that water molecule and become an alkene?
Well, it has more to do with the stability of the carbocations that are formed during dehydration. Tertiary carbocations, which come from tertiary alcohols, are more stable than secondary or primary carbocations, and that stability makes the dehydration of tertiary alcohols much easier.
So it's like the tertiary carbocations are more comfortable being on their own, making that dehydration process smoother.
It's a good way to think about it.
Okay, what about oxidation? Can alcohols be oxidized, and what happens when they are?
Oxidation is another important reaction that alcohols undergo. It basically means losing hydrogen atoms or gaining oxygen atoms. And the product of that oxidation depends on what type of alcohol you're starting with and what oxidizing agent you're using.
Okay.
Primary alcohols can be oxidized to aldehydes or carboxylic acids, while secondary alcohols are oxidized to ketones.
So oxidation is like giving the alcohol a makeover, changing its molecular outfit.
I like that analogy.
What happens to tertiary alcohols when you try to oxidize them? Do they just, refuse to change?
Tertiary alcohols are actually pretty resistant to oxidation under normal conditions because they don't have a hydrogen atom on the carbon that has that OH group.
So they're like little molecular fortresses, protecting themselves from those oxidizing agents.
You could say that.
We've talked a lot about alcohols now. What about those phenols? Do they have their own unique set of reactions?
Phenols have a whole bunch of fascinating reactions, mainly because of that benzene ring. One important one is electrophilic aromatic substitution. Remember how we talked about that OH group activating the benzene ring, making it more susceptible to electrophilic attack?
Yeah.
Well, that means that all sorts of electrophiles can come in and replace those hydrogens on the ring. You get a huge variety of substituted phenols.
So it's like the benzene ring is throwing a party and inviting all these electrophiles to come in and rearrange the furniture.
I like that analogy.
But are all the positions on the ring equally attractive to those electrophiles, or does the AOH group have a preference?
The AOH group is definitely not just watching the party happen. It actually directs those incoming electrophiles to certain positions on the ring. Because of resonance effects, those ortho and para positions, remember our molecular dinner party?
Yeah.
Those positions become more electron-rich, so they're more attractive to electrophiles.
So the AOH group is playing host, making sure those electrophilic guests get the best seats at the table. Can you give us some examples of these electrophilic substitution reactions with phenols?
Sure. One common one is nitration, where you add a nitro group, NaCnO2, to the benzene ring. You do that with a mixture of nitric and sulfuric acids. Another example is halogenation, where you add a halogen atom, like bromine or chlorine, to the ring. That usually uses bromine or chlorine in a suitable solvent.
So many different possibilities, so many ways to dress up that benzene ring.
It's pretty amazing the diversity you can get.
Are there any other reactions that are specific to phenols that we haven't talked about?
There are a few. Phenols can do some cool things because of something called the phenoxide ion. That's what forms when a phenol loses its proton.
Okay.
One of these reactions is Kolbe's reaction, where phenol reacts with carbon dioxide in the presence of sodium hydroxide to form salicylic acid.
But salicylic acid, wait, isn't that what they use to make aspirin?
You got it. Kolbe's reaction is actually how we make salicylic acid commercially, and then we use that to make aspirin and other medicines.
It's like a molecular chain reaction starting with phenol and ending up with a pain reliever. Exactly.
Are there any other reactions that use that phenoxide ion?
Yeah. There's also the Reimer-Tiemann reaction, where phenol reacts with chloroform in the presence of sodium hydroxide, and that adds an aldehyde group, CHO, onto the benzene ring.
So it's like giving the phenol a whole new look, a new functional group, a whole new identity.
Precisely. And we use this reaction to make all sorts of aromatic aldehydes, which are important ingredients for perfumes, flavors, and other fine chemicals.
It's amazing how these simple molecules can be transformed into so many different things. But before we move on to ethers, I have one more question about phenols. Is there any way to get rid of that OH group and go back to just a plain benzene ring?
You can actually do that. You can heat phenol with zinc dust, and it'll convert back to benzene. We call that reductive deoxygenation.
Yeah.
It basically removes that oxygen atom from the phenol.
It's like taking the phenol back to its roots.
Exactly.
Okay, let's talk about ethers now. We've covered how to make them, but what about their reactions? Are they as versatile as alcohols and phenols? Ethers are generally less reactive than alcohols and phenols, but they do have some reactions they can do under the right conditions. One important one is the cleavage of that CO bond using strong acids like hydrogen iodide or hydrogen bromide.
What happens when that bond is cleaved?
It breaks the ether molecule into two alkyl halides, basically undoing that Williamson synthesis we talked about.
Oh, okay. So it's like the ether is splitting back into its original parts.
Yeah, you could think of it that way.
Are all ethers equally easy to cleave, or does it depend on their structure?
Good question. It actually does depend on what alkyl groups are attached to. That oxygen atom, ethers with tertiary alkyl groups, are easier to cleave than those with secondary or primary alkyl groups.
Why is that? Are those tertiary alkyl groups just itching to break free?
It has to do with, you guessed it, carbocation stability. The cleavage reaction makes carbocations, and those tertiary carbocations are much more stable than secondary or primary carbocations. So ethers with tertiary alkyl groups are more likely to undergo this cleavage.
So it's like the tertiary alkyl group is winning that tug of war against the oxygen atom.
Exactly.
What about electrophilic substitution? We talked about how phenols do that. Do ethers do it too?
They do, but ethers are generally less reactive than phenols. That alkoxy group, ARR, in ethers still activates the benzene ring, but not as much as the ARH group in phenols.
So it's like the alkoxy group is a bit less welcoming to those electrophiles.
That's a good way to think about it.
It's amazing how these tiny little differences in structure can have such a big impact on how these compounds behave.
It really is the beauty of chemistry.
Okay, so we've talked a lot about the nuts and bolts of these compounds, how they're named, their structures, their reactions. But I want to switch gears a bit and talk about some specific examples of alcohols that are important in industry. I know we've already mentioned ethanol. It's a big deal in beverages and fuel.
Yeah.
But what other alcohols are out there making a difference?
Well, besides methanol that we discussed earlier, there's another one called ethylene glycol.
Ethylene glycol, does that ring a bell? Is it something to do with cars?
You got it. Ethylene glycol is the main ingredient in antifreeze.
Oh, yeah.
It has 2 hydroxyl groups, so it can form a lot of hydrogen bonds, which gives it a higher boiling point. That makes it perfect for preventing those engine freezing disasters in the winter.
So ethylene glycol is like the winter protector for our cars, keeps those engines happy even when it's freezing outside.
Exactly.
Are there any other alcohols out there that are like unsung heroes of the chemical world?
Another one that deserves a shout out is glycerol, also called glycerin.
Glycerol, okay.
It's a trihydric alcohol, meaning it's got 3 hydroxyl groups.
Okay.
That makes it really good at attracting water molecules, so it's used as a humectant in a lot of products.
A humectant, what's that?
A humectant basically draws moisture from the air and helps keep things hydrated. So you'll find glycerol in lotions, soaps, even food products to keep them from drying out.
So glycerol is like a little molecular sponge, soaking up that moisture and keeping everything nice and soft?
Exactly, a very important molecule for keeping things moist.
It's crazy how these alcohols are working behind the scenes to make our lives better. But before we wrap up, I'm curious about the impact of alcohols, phenols, and ethers on like a bigger scale. We've talked about their individual properties and uses, but what about their role in the world as a whole?
That's a great question. They're so common that they really do play a huge role in shaping the world. For example, in medicine, you've got alcohols used as solvents and disinfectants, phenols are in antiseptics and painkillers, and ethers used to be used as anesthetics.
So they're like a crucial part of how we stay healthy and fight off infections.
Exactly. And in material science, these compounds are used to make all sorts of things, from plastics and resins to textiles and adhesives.
So they're not just keeping us healthy, they're also literally building the world around us.
That's right. And we can't forget about agriculture, where alcohols are used as biofuels, phenols are used in pesticides, and ethers are solvents for various processes. They're essential for growing food and supporting a growing population.
Wow, it's like they're woven into every aspect of our lives, supporting our health, our infrastructure, our food. It's really incredible how these seemingly simple compounds can have such a huge impact on the world.
It really is, and I'm sure as we continue to explore the molecular world and develop new technologies, we'll find even more amazing uses for alcohols, phenols, and ethers. It really shows how chemistry isn't just, theoretical. It's about understanding what our world is made of.
It's like we've been on this amazing backstage tour of how these little molecules are actually affecting everything we do.
Exactly.
And speaking of everyday things, are there any other commercially important alcohols that we haven't talked about yet? I know we covered ethanol, the big one for drinks and fuel.
Yeah.
But are there others out there that are making a splash in industry?
Well, we already talked about methanol, but there's another one called ethylene glycol. Have you heard of that one?
Ethylene glycol, yeah, I think so. Does it have something to do with cars?
You got it. Ethylene glycol is the main ingredient in antifreeze.
Oh, right, antifreeze.
It's got those 2 hydroxyl groups, so it can form tons of hydrogen bonds.
Okay.
And that gives it a higher boiling point, which is perfect for, preventing your engine from freezing up in the winter.
So ethylene glycol is like the winter guardian for our cars, keeping those engines running smoothly even when it's freezing out.
That's a great way to put it.
Are there any other, unsung heroes in the alcohol world that we should know about?
Yeah, there's another one worth mentioning, glycerol. Or sometimes it's called glycerin.
Glycerol.
It's a trihydric alcohol, which means it has 3 hydroxyl groups.
3, wow.
And that makes it super good at attracting water molecules. So we use it as a humectant in a lot of different things.
A humectant? What's a humectant?
Basically, a humectant pulls moisture from the air and helps keep things hydrated. You'll find it in lotions and soaps, even in foods at times, to prevent them from drying out.
So glycerol is like a molecular sponge, soaking up all that moisture from the air to keep things nice and hydrated.
It's exact.
It's amazing how these alcohols are quietly making our lives better in so many ways. But before we wrap up today, I'm thinking about the impact of all these compounds, the alcohols, phenols, and ethers. We've talked about their properties and their uses, but what about their overall role in shaping the world we live in?
That's a really interesting question. They're so widespread that they have a huge impact on the world. In medicine, for example, you've got alcohols used as solvents and disinfectants, phenols and antiseptics and painkillers, and ethers were used as anesthetics.
So they're essential for keeping us healthy and fighting off those nasty infections.
Absolutely. And in material science, we use these compounds to make all sorts of things: plastics, resins, textiles, even adhesives.
So they're not just helping us stay healthy, they're literally building the world around us.
You got it. And then there's agriculture. Alcohols are used for biofuels, phenols are in pesticides, and ethers are solvents for all sorts of processes. They're critical for growing our food and keeping up with a growing population.
It's incredible how these compounds are interwoven into every part of our lives. They're supporting our health, our infrastructure, our food supply. Really amazing how these, seemingly simple compounds can have such a huge impact.
It really is, and I have no doubt that we'll keep finding even more amazing ways to use alcohols, phenols, and ethers as we learn more about chemistry and create new technologies.
Well, I think we've given our listeners plenty to think about today. We've journeyed through the world of alcohols, phenols, and ethers, exploring how they're structured, how they behave, how they react, and even their roles in our daily lives and in shaping the world as a whole.
It's been a real pleasure diving into this with you and exploring the mysteries of these incredible compounds. I hope our listeners are looking at the world around them a little differently now, appreciating all those molecular wonders that are hidden in plain sight.
Me too. And until next time, keep exploring, keep asking questions, and keep being amazed by the incredible world of chemistry.